One of the widely used routing protocol is OSPF. So such a widely used routing protocol needs to be learned in proper. So that's why we are having the second revision. We have gone through the entire features that are available in OSPF, complete features. One or two might be left. That's why we are going one more time with the presentation to fill all those gaps. Of course, yes, there are a few things which I have not shared, like sequence number and so on. I remember I have not touched those areas. We'll be doing those things while we go through this presentation. Now, open shortest path first uses an algorithm called SPF. That is what that SPF that you see there, second, third, and fourth characters in OSPF. O stands for open, which means this is an industry standard protocol, open, ready to use by anyone. There is no vendor specific. This is not belong to a vendor. This is open standard. It's industry standard. Every networking device will support this. And this protocol is coming under a type called link state. Link state routing protocol advertises the link status. What is sent in a link status? The status of the link, like whether it is up or down, and whether there is a area configured. If so, what is the area, and what is the mask, and the subnet means the prefix, and the mask, the timer, the hello timer, the lead timer. We have 10 and 40 for a broadcast or a point-to-point network type. We have 30 for NBMA non-broadcast and non-broadcast multi-access, and point-to-multipoint non-broadcast. Fine. Now these things like the area ID, the authentication type, the authentication string, stub, timers, all these things need to match when a router send hello to the other. If not, they don't form neighbor. So after they form neighbor, they advertise their database. Every router builds a database. When a new update comes, it comes with a sequence number. So a receiving router will compare the existing sequence number from the neighbor with the incoming sequence number. When the incoming is higher, the receiving router will update this database with the incoming update. So we'll talk about that procedure of updating the database in some time. So what I'm trying to say is every router has got a database. So once they say hello and know each other, they share their database in a summarized way. After which they fully get synchronized and they become very good adjacent router. Now what happens? This router which received the new database now run the SPF algorithm over the database. What does that mean? Find the shortest path to reach every destination and then put that path into the routing table. Actually, it will recommend it to the routing table, and routing table will use it if there is no other protocol with better at administrative distance. End of the day, it is the routing table that one which is going to decide whether the route will be there in the routing table or not. OSPF may recommend a number of things, not necessary to be seen in the routing table because there may be another routing protocol like EIGRP whose administrative distance is lower may also be providing the route information. So it is the routing table algorithm finally decides what route goes into the routing table. If you don't have multiple routing protocol, then for sure you will see OSPF's route recommendation in the routing table. So to maintain the routes, you need a routing table. To maintain the database, you need a topology table. We call it as link state database. And to keep the neighbors status up or down, to maintain the neighbor relationship, you need a neighbor table. Now in the topology table, if you see, the database will be identical within an area. In a topology table, the topology table will be identical for all the routers within an area. This is very important point that we should know. You may have multiple areas, but not every area will have identical database. Whether you summarize or not, it is not going to be identical. See, every area border, we do summarization. So you may think that because you are summarizing, the other area will not get the detailed database. Yeah, that is also there, but I'm telling you, even if you don't summarize, the other area will not have same database that you have in this area, because there are some LSAs that are not sent to the other area in the same form. For example, type 1 and type 2 LSA is not sent as type 1 and type 2 outside. It is sent as type 3. Then it is not going to be identical. So whatever you have in type 1 and type 2, there it is going to be in type 3 section. So in no way LSDB for all routes will be identical between areas. So only within area you can see identical database. So the reason why I should go for link state routing protocol is because it is the link state advertised. The routers can learn the complete topology. See, when someone gives the best, when my father gives the best and leaves this, he left the earth, he gave the best. He gave the best. And the child who enjoys that luxury will not know the pain behind, will not know the struggle, the negative things, the difficulty that he has gone through to earn that luxury to provide to his siblings. Because he is giving only the best for his children, so they don't know the reality of how to get the best from this earth, all the struggle. The child who gets this as an inheritance will not have the real picture of the world because he is not exposed. He is just given the luxury, a house, a car, but he did not know how this house and car has come, how much struggle one have to go through. Likewise, the distance vector protocol give only the best from the routing table, only the best. So the receiving router will know only the best route to the destination because the neighbor gave only the best. There may be many other routes to the destination which neighbor did not expose. So the receiving router will not have the full picture of the topology in distance vector protocol. Whereas in link state routing protocol, every time father goes to work, he takes the son. Son is seeing how much hard work his father is doing in order to get that blessing, in order to make life easier, luxury. So as he is seeing everything, he will know the pain behind buying every single thing for the luxury life. So he will know how to protect it also. Because he has got the complete picture of how this has come, and if he loses it, he has to do that work from zero level like his father, struggling. So he don't want to lose it. He takes care of the health, wealth, everything. Very nice. Because he has seen the difficulty, the hardship that father has gone through to get this, to give him. Likewise, every link status is advertised by this routing protocol to all other routers. As a result, the complete map of the data or the topology is the complete information about the network is seen in every single router. So now they decide which one to be the best route to reach destination by using OSPF's SPF algorithm and recommend that route to the routing table. What I'm trying to say is the routing protocol can make an accurate path selection because it has got the complete database with in its database, complete topology information in its database, complete full topology information in its database. OSPF has got full topology information because the link state advertisement, like the son who has gone with his father whenever father works, as he is seeing, he got the full information how difficult it is to live a life in this earth. So he will not fall because he has seen the fall and rise of his father. So he can take a best decision in this earth to live. Then he is a good father who has given this education. This is the good education that father has given. He has shown his son the fall and the rise, so that the son will never fall again like he has fallen. Good father. Likewise, OSPF provides the complete picture of topology by advertising every single link status to all router. So the router can compare all the paths and pick the very best. So an accurate path selection is possible only when you have link state routing protocol. Not only that, when a path fails somewhere in the down the way, immediately the advertisement, the path failure notification is flooded. As a result, the router can go to the database and pick the alternate path and recommend it to the routing table as soon as possible. No other protocols can be this fast in converging to the topology change. OSPF is the fastest in convergence because it has got the complete database. The moment, as soon as As soon as it finds a notification saying the path has failed, immediately it swaps with another path. It puts another path to the routing table. So very small downtime you will experience in link state routing protocol compared to any other. Even ISIS is also the same because ISIS uses the same SPF algorithm. It is a link state routing protocol. OSPF has got areas, and these areas, if you don't have, then you will not have control over the flooding of update. Because we have areas, any change that happen in a network, the change will be flooded, notified only to the member of that area, not to any other area member. As a result, the other area members are not getting disturbed. The flooding is not going to consume the bandwidth of every area. A small change that happens may not be relevant for other area members. That's why you have put them in another area. So this impact of change that happens is localized because we got areas. We do summarization at the border. How you got the border? Because you have area, you got border. If you don't have border, Bangladesh, Bhutan, China, Nepal, India. If you don't have areas, then you won't have borders. So because you have border, you have a summarization point, a place where they do immigration, a summarization point, right? So summarization point is important to summarize. Summarizing here and there, like you do in EIGRP and in OSPF. At least in OSPF we have some in between. Sorry, what I mean BGP. At least in BGP you have some borders between the autonomous system. But in EIGRP you don't have any areas. There is no grouping. Only one big group. There is no hygienic summarization there. You can do summarization anywhere you want. Not that neat. That's the reason why EHRP is recommended to use only if you have less than 100 hops. After 100 hop, EHRP by default won't support. You can increase by saying max hop command up to 255. You don't have such limitation in OSPF. So areas in OSPF is good. Areas in OSPF, we got backbone area, which is the center to which all the other areas connect. The non-backbone areas are called as regular areas. The backbone area is also called as transit area because one area cannot talk to other area without going through this. So as I said, backbone area is the center of all other area. And the number 0 area is dedicated for backbone. So no areas can talk each other without using area 0. No non-backbone areas can talk each other without using backbone 0. So backbone area, you can call it as a transit because neither it's a source nor it is a destination. It is used as a transit. Here it is. You can see OSPF area characteristics. Minimize the routing table entry. How? On C, D, and E, you summarize the networks So area 1 networks are summarized in C. As a result, A, B, D, G, E, H learn only the summary of area 1. The size of the routing table on the other areas are minimized. Not only that, if any change happens on the router F, the impact is only inside that area 1 area. Only those routers that are inside area 1 gets that impact, gets those information. They are the only one who's supposed to get the information. That's why you have put them in area 1. The other areas are not that much close to these routers, these networks. So they don't need really those small changes. That's why they are in different area. So this makes the protocol more efficient because you are not unnecessarily disturbing D, G, E, H, A, and B. The small changes that happens on F router need not impact those D, G, E, and H. Yeah. So it's like uh, it is like a small change, yeah, a small link failure, a very small subnet. That subnet has got some computers. They don't really talk to area 2, area 3 members. Very rarely they may talk. So such networks, when they fail, there is no point of advertising to the entire autonomous system. Giving to the members of the same area is enough. This is achieved through this area because you have areas you summarize on C. As a result, the small change on the F router is not flooded everywhere. That is what the third point says. The detailed LSA flooding stops at the area boundary. So for this we need hierarchical network design. This is why we have area 0 and every area connected to area 0. Router A and B, all the links of that router, if you see, they are all inside area 0. This one and this one area 0. This one area 0. This one area 0. They're all in area 0. But this one on the same router C, this link is in area 1. That is why they are called as ABR. When you have one link in area 0, the other link in other area, we call those routers as ABR. These routers A and B, you cannot call it as ABR because all the links are completely in area 0. They're not having any other area on the router. Only these are border routers because they got one leg on area 0, the other wire on non-area 0, non-backbone area. Fine. Next, when we talk about OSPF, this is the very first packet that is going between router to initiate the neighborship. If this fails, then there is no neighbor. If there is no neighbor, there is no advertisement of database. So they will not be a part of network then. So hello is the very first packet. Hello packets helps to discover neighbor. But to discover neighbor, the hello packets to become neighbor, to be discovered, the hello that I am sending needs to be an acceptable hello. Meaning, I need to send hello with the area ID, with the subnet mask on the prefix, with the hello timer, which will match with the neighbor's expectation. So the second point here says the router declares the neighbor to be up after checking certain parameters. That's what I'm talking about when we say certain parameters need to match what is set, the timer, the mask, the prefix, the area ID, the authentication string, stub, all these things must match. And only then the other one will accept this hello, which is the very first step for OSPF topology. Hello. Now we got different type of networks in OSPF, and then the network type is broadly classified as two. One is point to point, another one is broadcast. Broadcast can also be called as a LAN because one LAN is one broadcast domain. Yeah, one broadcast is one LAN is one broadcast domain. If you notice, this point to point will have only two routers, whereas the LAN may have more than two. That's why it is LAN. More than two connected via a Ethernet switch. For sure, LAN will have Ethernet wire, otherwise you cannot have LAN. Ethernet wires are multi-point, meaning you can connect to a switch and have more routers on the same broadcast domain, which is not possible in point-to-point. Point-to-points are serial links. You cannot have more than two devices because the link has got only two endpoints. So point-to-point adjacency is going to be different from a LAN link or the multi-point or the broadcast. So you can call this LAN link, multi-point, broadcast. All these are same. Broadcast type, broadcast link type, multicast link, multi-point link type, or LAN link type. This is going to have different adjacency experience than the point-to-point adjacency experience. So both are not going to be similar. Adjacency in point-to-point, adjacency in broadcast is not going to be same because here there are many routers, whereas in point-to-point only two routers. 100%, there is no third router in point-to-point. See, when we have only two people in the team, your experience, let's say it is A. Now when you join another team where there are 15 people in the project, you will have different experience now. When you were in a project where only two people, me and Rahma, only we two are in the team, so we have a very good understanding. Because we are doing this project together, we both are the responsible for this project, so we'll be in full sync. I'll share everything that I do, he will share everything that he has done. So we will be in sync so that there won't be anything duplication. I no need to do the same thing what he has already done. He will not do the same thing what I have done. So we equally, we work together and we finish a task. But when there are 15 people in a team and me and Rahman goes and joins the team as 16th and 17th, we cannot have that full understanding, full adjacency with everyone. Because there are 15 plus 2, 17 people in a project. And everyone will think that let him do, why we should do. And what I'll think, I'm just a newcomer in this budget, let them do. But they will say, hey, he has just come, let him do. Something like that. So there won't be proper sync. To avoid those confusion, there's going to be a designated router and backup designated router, the team leader and the manager. As a result, the confusion is avoided. Everyone in the project, the 17 members know what they're supposed to do now because the leader has said, this is what your responsibility, this is what his responsibility, this is what her responsibility. So he has divided the job. And when there is a change, I notify to the team leader. For example, I'm sick. I cannot finish a module. I call the team leader, I say, sorry, I cannot. Now, team leader will talk to others and share the load, which is very easy to do. Other than me going to every other 16 people and please you do. One will say yes, but he will not do. The other will say no, straightforward. Sorry, I cannot do. My burden is already too much. The other person will say, okay, let me try, but I'll try, something like that. So then, the project is not going to be completed as expected. So it is good to have a leader when we have too many. Likewise, we have a designated router to which everyone will report. And designated router reports to others about the changes. So as a result, there is no duplication, there is no delay, there is no confusion, there is no loop. So what I'm trying to say is only to the team leader everyone reports, meaning they will have full adjacency. Within the team members, they will have only two-way relationship, meaning they won't be discussing anything about the project, but they know he is in our project. Everyone knows that we are all in the same project, but whenever there is a problem, whenever there is an update, whenever there is something to be notified, will be always notified directly to the DR, not to the other members in the team. So which is good, which avoids duplication. Otherwise, if there is no team leader, I need to go to all 16 members and say, what if two people does the job what I'm saying? Actually, only one has to do in my absence, but there are two people doing my job. Then it is a loop. It's a duplication. It's a waste of time. To avoid all this thing, we have a team leader. We have a designated router. What if the designated router fails? We have a backup designated router to take the role of designated router. As long as the designated router is available, the backup designated router will be a passive designated router. Passive. It won't give any outputs, any commands, any any uh, any updates. It's only the DR who sends the update. Backup designated router simply collects the update. Whenever any change happens, everyone notifies the change to both DR and BDR at the same time. The address that is used to notify DR is 224.0.0.6. Two DRs. To all the DRs, BDR and DR. And the DR will use 224005 to notify to others. DR others. So between the other members, there will be only two-way relationship. I know him and he know me. That's all. But they don't talk anything about the project between them among them. They only speak to DR and BDR. The routing table update and topology informations are passed only between adjacent router. Means fully adjacent router. Only to the DRs. Only between the fully adjacent router. Once the adjacency is formed, the LSDB is synchronized by the exchanging of LSAs. LSAs are flooded reliably throughout the area or network. So within an area, the type 1, type 2 LSAs are flooded. Type 1 LSAs are the one which is between every router LSA generated and sent to every router. Type 2 LSAs are sent from DR. We just saw that the DR is the one who was responsible for giving the routes to everyone, giving the informations to everyone in that LAN. Others cannot talk to each other. It's only through DR. So there is need for a type 2 LSA. And if you have these two LSA, that is enough for an area to be synchronized. Type 1 and type 2 is more than enough for that area network to get synchronized with all other routers in the same area. Open shortest path first is the algorithm proposed by Dijkstra. Dijkstra's algorithm is what we use here to build the link state database. We have LSAs and LSUs. We have LSAs and LSUs to build the database. Once the database is built, the router position itself in the database. Again, I want to repeat. The database is full of what? Full of information about the other routers and the link status. So in that database, definitely you will find your own router as well as the other routers. So position yourself in that map and see how far the other networks are and what are the best paths to reach them. And put the best path into the routing table. So the best path is determined based on the cost to reach those destinations. Cost is calculated based on bandwidth if you don't do it manually. More the bandwidth, lesser is the cost, cheaper is the cost. The total cost to reach the destination should be lower, should be less. To be picked as the best path. Now this is a kind of flowchart explains you the path selection. Assuming each link is of same cost 10. Now for X to reach C, this is the best path because it's only 10. If you come this way, it is 20. Likewise, to reach F, this is the best path because it is 10 plus 10. If you come the other way, it is 10 plus 10 plus 10, which is 30. It's going to be 30. So the binary tree algorithm, which is also called as shortest path first algorithm, Dijkstra's algorithm, picks the best path by calculating the path cost. Now here is the flowchart that explains us how the link state database is getting updated. When a new advertisement comes, the receiving router, if it is a fresh router, it will not have any database initially. Nothing will be there inside the database. So if there is no entry in the database, so whatever comes in is going to be added to the database. So updates, not updates, the link state update. Link state update is collection of a lot of link state advertisement. The link state update is now added to the database. After adding, the router sends the acknowledgement from to the neighbor who sent this update. After that, it floods the learned update to the downstream routers. Very, very nice, very nice. Master router sends its DPD to the neighboring router, to the slave, let's say. Now slave will not have anything, so whatever he receives, he updates to its database and send acknowledgement to the master. Not only that, the slave also floods the information to his downstream. The slave will have some other connections, right? The other direction, downstream. He floods the information and then recalculates, it runs the SPF algorithm, put the routes into the routing table. Now, this happens even on the master side when the slave sends the update. So master will also learn the routes in the database and send the acknowledgement and flood the database, the LSU, to other downstream links and recalculates the routing. Now, let's say I get a LSA or LSU. I'm checking whether my database is empty. No, it's not empty. It has got some information. It's not empty. I do have something in my database. Okay, if I have something in my database, what is the sequence number? The sequence number in my database and the sequence number that is coming, let's say sequence number 80 is coming. The sequence number that I have is 70. So it's not same. If it is not same, is it higher? Yes, it is higher. Incoming sequence number is higher. If it is higher, which means the incoming update is the latest. So it goes to the database, adds it, because it's new root information. It adds it, it's an updated one. Send an acknowledgement to the sender, flood the information to the downstream, and recalculate. What if the incoming sequence number is same? Both are 70. If both are 70, ignore, simply ignore. Now what if the sequence number is not higher, meaning you have 70 but the incoming is 60? If it is not higher, then the sender is not updated. You got an update, latest one. So you are supposed to inform the sender, the source, about it and then end the process. This is how the links to database is getting updated time to time. About the sequence number, We'll see in the next chapter. Now, as soon as the change happens, the change is quickly notified to everyone as a triggered update. Not only that, OSPF also does a periodic update every 30 minutes. Every 30 minutes, they notify about the existing condition of the database. Whether the change happens or not, in order to make sure that we are all in sync, it notifies every 30 minutes periodically. The entire database, a DBD is sent every 30 minutes. Right. So other things like two-tier hierarchy network structure, which reduces the flooding of LSA, which localize the impact of topology change, which helps to provide a summarization point. All those things we have seen in this chapter. So we also saw that it is the Dijkstra's algorithm which calculates the best path by adding the path cost. Path cost can be given by us manually for every path. If you don't do that, it will do auto path cost based on the bandwidth. More the bandwidth, lower the cost. That's a wonderful thing that you have in OSPF, not in ISIS. In ISIS, there is no auto calculation. What I mean is, it is going to definitely calculate all the path cost automatically, no doubt in it. What I mean is, based on the bandwidth, deciding the cost is not in ISIS. If you don't provide cost in OSPF, the link cost is determined automatically by taking the bandwidth. But in ISIS, if you don't provide manually the cost, each link cost is considered as 10 in ISIS. Whether it is fast Ethernet or gig Ethernet or a slow serial link, cost is going to be 10 for each link. So if I have 5 links, it is going to blindly take 50. I may have 2 paths with 5 links. One path may have gig links, another path may have fast Ethernet. But according to ISIS, both are same. Because according to ISIS, each link is 10 cost. You don't do calculation of cost as per the bandwidth. Anyway, when we go to ISIS, we'll talk about that. Now, that's the major difference. So I just explained. Most of the things are similar to OSPF. See the last one. After the LSA entry ages, the router that originated the entry send an LSU about the network to verify that the link is still active. The LSU can contain one or more LSU. That's what is LSU? One or more LSUs together. So there is a age out time for every link update, link advertisement, link state advertisement. So whenever the age out happens, it will check whether the link is available and then refresh it, resend it. We'll talk about this thing in detail in coming chapter or the following chapter. Right. Open shortest path first, packet types. We have 5 types of packets in OSPF. 5 type of packets. Hello is sent every 10 seconds if it is in a LAN environment, not an NBMA. In a normal broadcast or point-to-point environment, hello is sent every 5 seconds. Sorry, 10 seconds. You know about database description during the adjacency as well as when an age out happens, as well as the periodic 30 minutes. Link state requests are sent whenever there is a need for clarification on particular prefix destination sent. So when a DBD is sent, an acknowledgement, the type 5 is sent, link state acknowledgement. When an LSR is sent, the receiver will send an acknowledgement. When an LSU is received, the receiver will send an acknowledgement. LSU is the response of LSR. Link state request is a query. Link state update is the answer to the query. These numbers that you see 1, 2, 3, 4, 5, they are not numbers. They are all they are numbers, but they are not simply serial numbers. This is the number given to this type of packet. 4 means link state update. 2 means DPD. When you capture using Wireshark, you will see these numbers. In the IP header, listen carefully. When you capture with Wireshark, you will have data link header. You will also have Internet Protocol header, the layer 3. In layer 3, if you see the protocol field, here it is, protocol field with ID 89, it means that the next layer is OSPF. It means that next layer is OSPF because the picture is drawn like this. Don't think, that this entire thing is inserted into the layer 3 header. No. The picture looks like that. What does it mean? It means that layer 3 header knows that my payload is OSPF. The next layer is not transport layer. Next layer is a part of layer 3 only, but that is seen as the next layer. There is no UDP or TCP for OSPF because it's a layer 3 protocol. So the payload will be immediately after, means what is payload? The information about this OSPF will be immediately after layer 3. Like a layer 4, you will see OSPF with a version. Version 2 is IPv4 version 3 is IPv6. And then the packet type we just learned here, this packet type 1, 2, 3, 4, 5, 6. And then the packet length, the size of the OSPF header, the router ID, the area ID, checksum to provide integrity, authentication type 0, 1, 2, authentication string, and then if it is OSPF hello packet, you will see router ID, area ID, sub type, subnet mask, all those informations like neighbors, all those informations as data. If it is DBD, data will be different. If it is LSA, LSU, data will going to be different. So the packet length is all based on how much of data is carried. You will not have the same packet length for all type of data. Sometimes DBD will be small, sometimes it will be big. Sometimes LSR will be small, sometimes it will be big. You cannot. It depends again what it is sending, how much it is sending. If you see between the neighbors, the hello packets are sent, and these are the things that are supposed to match with a neighbor in order to form neighbor. Okay, so we are going to enter into the adjacency state. Before that, let's go for, and this adjacency, um, adjacency between point-to-point router, adjacency between LAN routers, broadcast, meaning multi-access router, is slightly different. See, in point-to-point, only two routers, whereas in multi-access, meaning when we have a broadcast domain in the middle with many routers, we all know there is a DR-BDR election, and there will be some routers called as DR others. One will be called as BDR, another will be called as DR. So adjacency cannot be same in point-to-point and multi-point because there is no DR-BDR in point-to-point. So let's see how this happens in a point-to-point network first, and then we'll talk about the multi-access. In point-to-point, from the down state, one of the router comes first. Using the router ID, it sends a hello packet. It sends a hello packet. The receiving router verifies the parameters such as area ID, authentication, subnet on the link, and so on. It also knows that this is sent by router A from the router ID. So it learns router A as a neighbor as well as the neighbor list of A. We call it as init state, meaning B has known this A. B knows A very well now. B knows A. So this is actually by using a multicast address, the hello is sent. We all know 224.0.0.5 is what the only address that is used for sending hello, whether it is DR or BDR or no DR, BDR, master slave, whatever. The only address that is used to send a hello is 5. Now B gets a turn to send a hello. B now sends a hello with the list of its neighbor with all of the parameters, and the A, after verifying parameters, agrees B as a neighbor and adds B's neighbor in A's neighbor list. Sorry, A's database. Neighbors of B now known to router A. Neighbors of A also now known to neighbor B. But A and B are the direct neighbors. The neighbors of B will not be there in the neighbor table of A. The neighbors of B and the neighbors advertised link information, all those things will be seen in the database. Anyway, as of now, it only knows that B has got some neighbor. But what A do not know is what all the neighbor of B link status. That will be learned through the DVD, which is coming after this. So now A and B knows knows each other. They know each other. We call this two-way state. And A and B now needs to decide on a role called a master slave, if it is point to point. Master slave. One will be elected as the master, the other will be as a slave based on the priority. No, sorry, no priority is considered In a point-to-point environment, priority is not at all considered. Very important. Priority is not a matter. Even if you set priority, it is of no use. You are allowed to set priority, no doubt in it. You can set priority, but it is of no use. Priorities are only for broadcast environment. In a point-to-point environment, it is only based on the router ID. It's the router ID which is going to decide the role, not the priority. So the one with the bigger router ID becomes the master. Am I audible? Okay. Thank you. Thank you. So yes. Recording is on. So only the router ID matters in a point-to-point network, in a serial link. So the one with the bigger router ID will say we are masters. The one with the lower router IDs will say we are slaves. We are slaves. So with this, they conclude who will initiate the DBD. This decision is what called as start, exchange start. This is opening the gates to start exchanging the database. So we call it as start state. All right. So the one with the higher router ID says, hey, I'll start the exchange because my router ID is higher. Fine. Now, router DR exchanges the DBD. We call it as DBD because it's a summary of LSDB. And for which this one, the left hand side router, will share acknowledgement as well as it will share the DBD of its own. Yes, I will. We will see that. We'll capture and we'll see that. And then the exchange state is where the LSR and LSU is shared between these two routers. Link state request. See, because it's a DBD, not the entire LSDB, because it's a summary, because it's a DBD that is sent, the exchanged DBD may not be that clear sometime. So they ask for some queries. They ask for some details about some networks, which is called as LSR. As a response, LSU comes with the details that has been queried. We call this as loading state. At last, the acknowledgement is even sent for this. See, after DBD acknowledgement is sent, after this LSR LSU acknowledgement is sent, and it reaches full state, meaning there is no more query to ask. So they are fully synchronized. Whatever the left router knows, the right router also knows. Let us see these things in capture. Only these two router. This is going to be, one is going to be master, other one is going to be slave. According to what we have learned, this will be the master and this will be the slave, because this has got the bigger router ID. So first I'll start one and shut down the interface so that you can see everything in debug as well as in the capture. I don't want to start the capture now. I'll just shut down this interface as soon as the router comes up, so that we'll capture everything from the beginning. Interface serial 6/0 shutdown. I believe the IP address are still there, which I configured earlier. I'll check once on router 1. Show IP OSPF interface brief. We do have OSPF running on this 2 interface, but if you see here, this is down because we have shut down the port. Configuration of OSPF is there. It is in OSPF area 0. Process ID is 1. Show IP OSPF neighbor. There is no neighbor. Show IP interface brief. The IP addresses are like this. This will be the loopback. I think R2 should be ready now. I'll shut down that port also. So no negotiations, nothing. It's clean, both side down. See, administratively down even here. I'm going to keep it ready to bring it up. I have not said enter. I have not said enter. I'm not saying enter now. Let me do debug IP OSPF adjacency. Likewise here, do so both sides we have enabled debug, and I'm keeping no shutdown ready. I'm not hitting enter because I need to start the capture Wireshark. It is link type HDLC. We are not running PPP there. If you want, you can run PPP or frame relay or ATM, but I am running only HDLC. And it is between the router 1 and router 2, serial 6/0. Start capturing. And you won't find anything coming in between because we have put the interface down. So this is going to be blank. Let me bring it under the frame of recording. Frame of recording. All right. So let us go and unshut these 2 ports, router 1 and router 2. Done. As soon as I hit enter, you see CDP is going. And update, acknowledgement, everything is done. So the neighborship is already up. DBD, everything is sent. So I'm going to stop the debugs on both Wireshark as well as router. Do and debug all. Fine. Now let's see in the debug first. And this is router 1. As soon as I say no shutdown, what has happened is the interface came up. Build router LSA for area 0, router ID. So this is saying this is my router ID and some sequence number for the process ID 1. So it is building some database. Whatever it has got locally, the local link state information it is building. And always the init state will not be able to capture. Sometimes some operating system shows, but mostly I have seen only it shows only two-way. So you can see the two-way communication to what does that mean? It means that router 1 already knows about router 2. So the hello is already initiated from R2. Let's go to R2 and see whether init is seen. Sometime you can see init. Unfortunately, here also I am seeing only two-way. Two-way communication to 11 to serial state two-way database. So here we see this is router 1. Router 1 says I know that guy. That guy also says I know him. Both knows each other. So now they are preparing their database to be exchanged. Send the DBD to serial this, receive DBD it's actually not original DBD. We will definitely go there. Let's finish this one, okay, please. We'll finish this one because you cannot correlate that and this together. We will see there. We'll see there. See this order. You know the order. First is init two-way, and now it is planning to start the exchange. So immediately one router will say, "Hey, we are slaves. We cannot do this exchange." In the start state only they decide. And when this is saying slave, and that says we are not slave. Same in the start state. And now what happens is the exchange need to be started by the router 2. So this is the original DPD. After exchange is the real payload. Send the DPD to so and so with this sequence number. If possible, I'll show you the sequence number there in the capture and Wireshark. And also on the other side, DPD is sent. And after that, there will be LSR and LSU. See, there is a link state request asking for some details. You don't see what detail it is asking for here, but in the capture you will be able to see. And that one also sends some request. So both exchange few things and they receive LSU from the other side. Each other they receive the updates. And after that they are fully synchronized. There is nothing more to ask. Fully synchronized. That's why you see loading to full state on either side. Cleaning up the database exchange. Fine. It saves to a temporary place and exchanges and then cleans up. So on the command line, this is how it is. See, you saw a master slave role, but that is not forever. It's only during this adjacency state, this master and slave. But after this, if you go and check the neighbor, there is no master, there is no slave. Show IP OSPF neighbor. There is nothing called master or slave mentioned here. Usually, if there is something like DR, BDR, DR other, this is where it will show. For master slave, nothing will be shown because the role is temporary. But DR, BDR is not temporary. Even after the adjacency, you will find DR, BDR continues. Now, let's go to the Wireshark. And I just want to adjust this because the previous training was Wireshark Cisco Bangalore. So I have a lot of things here. Okay. Okay, all in one page. Let me zoom a little for you. Is the font size manageable?
Yes.
All right. So here we see the very first hello going from router 1, initiating to 224.0.0.5. Let's see the hello packet first. How do I know it's a hello packet? Even here it is said hello packet. And let's go down. OSPF header. Okay, I was talking about the protocol field. You see protocol field, it says in layer 3. I got IGP OSPF 89 as the next layer of information. That's what you see here down. So when you open that, it says version 2 means IP version, OSPF version 2 means IP version 4, supporting the older OSPF, you can say. And it's the type 1 message, hello packet. The packet length is 44. The packet length is 44. But I see here the length of the packet is 80. What is the difference? See, only OSPF header length is 44. Other layer 3, layer 4, layer 2 informations, they altogether is 80. This is total length. So you can see more than half is OSPF information in this packet. You see, 20 byte is for layer 3. So somewhere around 76 is the total length plus some extra encapsulation, so it becomes 80 total. No, sorry. 76 is what the total length of the packet. 76. And yeah, correct. As I said earlier, it is 76. And then OSPF is 44 in that. And the balance 4 is some additional encapsulations here and there. Now, router 1 says my router ID is this. And I'm from area 0, I'm backbone. This is my checksum value. No authentication. And now when you open this one, This is also part of hello packet only. It says my mask is this. Earlier, if you see, it was only saying router ID and area ID. There is no network information so far, like 10.12. It says this is my net mask and my timer is this. And this packet is not from a stub area. This is capable of receiving Typhi LSA, external LSA capable. LLS data block present means layer 2. And the priority, router priority is 1. I told you in point to point it's of no use, but it is shared as a standard. OSPF hello should share the priority. Because it is standard, even though it's a point to point DR, BDR information, that field is available, but it is not going to be in use because it's a point to point. And this and all will not have anything useful as of now. This TLVs, additional extended TLVs, is only when you do some extension to OSPF. Like you carry some BGP community or yeah, like that. In segment routing, we see that. In service provider track, you learn it. Now, this is what OSPF hello packet look like. Now, the second hello is coming from router 2. Wait, in router 1, if you go back to router 1, the hello packet, you don't see any neighbor list because this is the very first hello. You don't see any neighbor information in the header. Okay, now let's go to router 2. Router 2 says it's me, 2222. See, the packet length is same because it's a hello packet. This is my subnet, this is my time interval. Unfortunately, the previous hello which went from router 1, router 2 was not available to receive. It didn't learn. So it's like router 2 only the one who is talking first. Now router 1 sent the hello packet back. Now you see router 1 knows the neighbor called 22. See, router 2 was not knowing about any neighbor because router 2 did not hear the previous hello which was in packet number 5 from router 1. It didn't learn. Router 2 was not ready to receive. So it is the init state from here. This is the actual init packet. And this is the two-way packet. It says, hey, I know my neighbor is 2222. Router 2 is saying my neighbor is 2222. Now the packet length is... Yeah, no. This is the 8th packet after I say no shutdown. When I say no shutdown, a lot of CDP packets is Cisco Discovery Protocol. Okay, if you want to see only OSPF, you just filter with OSPF. Okay, so don't worry about that 8, 5 and all. That is the number of packets that was going in between the router. In that, 5th packet is OSPF, 8th packet is OSPF, 9th packet is OSPF in the capture. That's not OSPF packets. Those 1 to 5, as 1 to 4 is not OSPF packet, so ignore that number. Huh? I just said 8 for you to locate the line. The 5 was the first hello from router 1, but the problem is router 2 was not ready that time. Now router 2 is sending its hello in the 8th packet in the capture, 8th in the capture. For OSPF, it's the first packet. For OSPF from router 2, this is the first packet. In that hello, router 2 is saying my name is 22, 22, 22. There is no neighbor mentioned, which means router 2 do not know about router 1. So it's a init packet. And router 2 now sends the hello, and in that hello, it also say this is my neighbor. This is my neighbor. Okay, so router 1 knows about router 2 now. Router 2 earlier knows about router 1, and now both know each other. So they decide who is big and who is small. So router 2 only first sends the DBD. You see here? It is only router 2, the one with the bigger router ID, only starts the DBD first. So in the DBD, if you open, this is DBD, database description, the packet in this 32, OSPF. See, it's not the same length. Earlier we saw 44, 46, now it is 32. This was having, the one with the neighbor was having 48. Hmm. And without neighbor was having 44, 48. And then now the DBD is having only the DB database description information, not the other informations like neighbor and all. So this is having 32 length. And the source router is the router ID. It is source router. But in the previous thing, it was just a hello packet sending with the source. Now this is DBD. Now, if you do go down, you will know that whether it is DBD or hello. Here it very clearly says it's DBD. See, in DBD, what it shares? It shares the MTU value. It shares the capability of the router, what it is capable of and what it is not capable of. And also it shares the uh, other information like this is the master. MS means master, M means more, I means init. Not much clear about these infos. Next is you got a sequence number. Sequence number matters. This is the sequence number of this packet. Now, this is just extended value, not that important for now. So this is what you see in DBD. But again, the DBD in detail is coming later. So this is the first DBD. And router 1 is also sending such DBD, but the sequence number is not the same. Definitely it won't be same. Other things are almost same. The router ID is different. And then again, router 1 sends another DBD. You will have DBD in more detail soon. Okay. What is the frame now? Which I selected. I have selected frame number 13. Let's go to 14 now. See 14 DBD. For each link, the status will be advertised where it is. Look at this. LSA type 1. Um, it is talking about the link state ID 2220. It is advertising the loopback and what it is capable of. For each network, we don't have much network, so you see only one now. On router 2, we have only one loopback interface. It is advertising about the loopback. See, 10 network is directly connected. There is no need for advertisement. This knows the link state of this link. This knows the link state of this link. No need of advertisement. So for 22, it is advertising, saying this is the link ID, this is the IP address of the link, and so on. The DBD. Now let's see from router. What's the frame ID? I select 14. Okay, let's go to 15. If you see 15, 15 will be advertising about 11, 11, 11. Okay, this is an LSR. Okay, router 1 is sending an LSR asking some detail about something. Okay, now DBD is coming from router 1. Router 1 will be advertising about 11, 11, 11. Where it is? Maybe in the next packet. This is router 2 sending an update for the LSR which was asked earlier. And what is this? This is request from router 2. Where am I? Frame number 18. Okay, frame number 19 from router 1 will be sending LSU update packet with the link state of 1111, the loopback router, link state of that. Likewise, we see the LSAs and LSUs and LSRs, say LS acknowledgement. Acknowledgement is going between these two router. Acknowledgement for this network, it has received 22. So likewise, the acknowledgement goes on bidirectional. Full state is achieved. So we don't have many network, otherwise so we will see more in the update. Let me quickly add some more and then I'll start the Wireshark. So I'm starting the Wireshark once again and I add more network to show you. All right. So as they are keep on sending hello packet, I'm going to router 2 to add another loopback 122, IP address 122.122.122.122.255.255.255. IP OSPF 1 area 0. See, as soon as I hit enter, you see there's a trigger update going from router 2. Look at this. Router 2 is sending an update, and the further acknowledgement is immediately sent. Let's stop this. Router 2 says it's an update message. What is there in the update? It is about a network called 122. You see, it's about a network called 122 whose mask is 255.255.255, and the metric is 1, meaning cost is 1. That's local cost plus the point-to-point link, the serial link cost on 10.12 is 64 for OSPF. For the serial link 1.5 meg, no serial link, the metric is 64. So this is what the information that immediately it shares when I created a network and advertised in OSPF. This is the total metric to reach from router 2 to reach 11, 11, 11, 11. This is the total metric to reach 64. Likewise, to reach the other end of the wire 10.12, because we have serial, this is the metric. Let's see the acknowledgement packet. The acknowledgement packet is an acknowledgement. It says I have received your, the previous one. Say the checksum value 0xED44, 0xED44, which matches on both. And it's an acknowledgement for that. That's not altered. That provides the integrity. So this is how the DBD will look like. Anything you want me to show? I can show you. Rahman, are you there? Arul? Arul, are you there? Okay. Rahman, are you there? I was just checking whether I'm connected because I was not hearing from Rahman.
Yes.
So, sorry, you were in mute, I think. Do you have any question? Should I show something?
No, it's fine.
Okay. So far what we have seen is in a point-to-point environment, how this works. Now, next is in a multi-point environment, multi-axis environment. Let me stop this to running. In a multi-axis environment, see, there is going to be a slight change in the X start state. Here in the X start state, we saw there is a master, there is a slave. Whereas in multi-axis environment, because there are more routers and the hello packets that are going in between allows every other router to know about the router ID of this router. So every router knows the router ID of the other router. By comparing the router ID, one router which thinks that this has got the bigger router ID comparatively will declare itself as BDR. Very important. The one with the bigger router ID, first it will check the priority. The one with the bigger priority declares itself as BDR, not the DR. No DR election. DR is not elected directly. DR is not elected directly. First, it need to be a BDR. So the one with the bigger priority, if priority is a type, the one with the bigger router ID becomes a DR, designated router. Designated router, DR. After that, becomes the BDR. The one with the bigger router ID becomes the BDR first, backup designated router. After, it will wait for, it will just listen one more time for all the hellos, and then it declares itself again as a DR because there is no other router. I stayed in BDR, I was checking for other router, hello packets. That's the procedure. Okay, after becoming BDR, it has to listen again once whether any other router ID bigger to be on safer side. That is how it works, and then it declares itself. It promotes itself to designated router from BDR. So initially it will be in a BDR state. The one with the bigger priority or the router ID becomes the BDR, and then it promotes to DR. And now the next biggest router ID router will say, then I'll become a BDR. So if priority is there as a type break, it will not consider the router IDs. If there is no priority, then the router ID matters. There is no, the default priority is 1 on all the router. So a DR is always promoted from BDR, and when there is no BDR, the router will, the next biggest router ID or router priority becomes the BDR. So what is next? After this, the adjacency is formed, meaning every router will advertise Every router will advertise their database to DR and BDR. Actually, first the DRs only will advertise. First, the DRs will advertise, and all the others will also advertise the DBD to DRs. That is how DR will have full relationship with others. So this will keep continuing till the DR gives everything that it knows about others. So if one other want to give something to another other, it has to go through DR. So whenever DR gets new LSUs and DBDs, it will be keep on sending it to all others using 224.0.0.6. That is the big difference in this extart state and an exchange state. In extart state, there is a DR, BDR, and DR other elected. In the exchange state, the distribution happens only between the DRs and the other, no between others. Others will be in two-way state. Two other routers will be in two-way state. What is other router? The router which is neither DR or BDR. They're called as other routers. So if I have two or three other routers, they're all stopped in two-way relationship. The others will have full relationship only with DRs. When I say DRs, it includes BDR. So exchange will take a while here because there are many routers. All routers will be forming full adjacency with the DR. So now new details every time DR receives, it needs to update the others. Again, they form full relationship. Again synchronization. After a point of time, there is nothing to share. They are fully synchronized. No LSR comes. All LSR has been answered, and they reach full state. This thing I'll show you in demo in our next class.